All right, thanks, Sasha, for the introduction, and thank you to the organizers for inviting me here. It's been a super fun workshop. I'm enjoying every minute of it. The only issue is that the cold deadline is in a couple of days, and that's taken away a little bit of my enjoyment and a bit of sleepless nights as well. So if I seem a little incoherent, yeah, that was the plan. Yeah, it's sabotaged my cold paper. Take them out. You could have had it before the ICML deadline. It would be more fun anyway. Okay. All right. Okay. So let's get started. I'm going to be talking about adaptive methods for non-concept optimization. And I was extremely fortunate that the organizer scheduled Rachel to talk before me because she introduced everything about adaptive methods. So that made my job easier. So here's the agenda. So I'm going to be talking about three different things. The first part is some stuff which people have alluded to already in this workshop. So we're going to be analyzing some modern non-context optimization methods like ADAM and RMS-prop, and actually show that they can fail to converge in very simple, even context optimization settings. In the second part, we'll try to salvage these methods a little bit and kind of bound the extent of failure. We'll show that maybe they might fail, but the failure is bounded in the sense that they might converge to some neighborhood of a first order optimal point. And then we'll also, based on these ideas, we'll also give a new method called Yogi, which has a significantly better practical performance than ADAM on basically everything that we have looked at so far. And the third part is super new. It's work that was primarily done by actually a student of Stephanie's here at MIT, Matt Stabe. So we'll actually dig into these newfangled optimization methods like ADAM and RMS-prop a little bit deeper and try to uncover the mysteries of how they work, of the exponential moving average that they use in their definition. And basically, we'll show that this specific feature of these new methods actually enables them to escape saddle points in non-context optimization and reach second-order optimal points. So maybe that's why they are useful in practice. We're not claiming that this is the reason, but it actually gives some hints about why they might be useful in non-context optimization. Okay, so let's get started. So the first part is a paper which appeared in ICLR last year with Sashank Reddy and Sanjeev Kumar. All of us are at Google. So here, as I mentioned, we're going to be analyzing the convergence of ADAM. There's going to be a few very, very basic introductory slides, since my preferred method of creating a talk presentation is to copy-paste somebody else's slides. So that's what I've done here. Sashank's slides are here. So as Nati mentioned in the panel discussion yesterday, not only is optimization central to machine learning, machine learning is optimization. So I don't need to explain why optimization is important. And also, again, everybody knows that non-context optimization is hard. So, okay. So we'll specifically what we look at is stochastic optimization setting, which is the standard thing in machine learning, where we want to train a model to minimize the population risk. And so because we're looking at optimization methods, we'll be looking at things like suboptimality gaps, how far the solution that you return, how far it is from being an optimal one in terms of the loss. And the way we'll analyze these things is via online learning or online optimization, where we'll connect the gap in optimization to the average regret. Okay, so I'll make these things more precise as we go on, but that's roughly the setting we're going to be working on. So this is again going to be like a rehash of things you have seen already. So everybody knows SGD. So here you optimize your parameter vector xt by moving in the negative stochastic gradient direction with some step size. This is obviously like the method of choice for training any deep learning model these days. So what people found is that, okay, maybe sometimes it doesn't, and maybe it's a little too conservative. The step size decays like 1 over square root of t, and at least in theory, and then maybe and people want to be greedy and try to converge faster. So things like AdaGrad were developed, where again Rachel already talked about this in the last talk, so it's a little easier for me to explain. So here what you do is you scale down. So again, this is going to be per feature, the per feature version of AdaGrad, where in each feature you scale down the partial derivative along that feature by the square root of the sum of squares of all the partial derivatives in the past. So this actually is very nice to do when you have features which have different scales. It also actually was originally developed to handle very, very sparse features, where some features appear very rarely. In such situations, AdaGrad is extremely useful. And by far the most, I guess, influential method in training deep networks these days are these new methods called like ADAM, RMSProp, AdaDelta, and there's like more and more of these. There's something called NADAM and PADAM and whatnot. But the main difference is it tries to imitate AdaGrad in the sense that it takes the gradient and scales it down by square root of the sum of squares of the past gradients. But it recognizes that since you're working in a non-convex setting, maybe gradients that are too far in the past are not very useful. So instead of taking a uniform average over all the past gradients, it does like an exponential moving average. Okay, so it scales down gradients that are too far back in the past by an exponential factor. All right. So I'm going to linger on this for just a second more, so that this update rule is kind of entrenched in your mind, because this is exactly what we're going to be the object of study for the next, 40 minutes or so. Okay. All right. So this works very well. I believe the last time I checked, I think the ADAM paper had maybe 3 or 4 times as many citations as AdaGrad paper, even though it just came out just a couple years ago. So it's very influential. Okay. So the key feature here is the exponential moving average, and this is what we're going to study in more detail. All right, so here's a very simple example which explains why things like ADAM might not work. So imagine that you're in a very, very simple convex optimization setting where you want to optimize some stochastic linear functions over let's say one-dimensional functions even over the interval -1 to +1. So these functions are as given below. So you have 20x, which arrives with the function. You see the function 20x with the probability 1 over 20. You see the function. Sorry, this should have been -x. I'm sorry. Okay. You see the function -x with probability 19 over 20. So if you compute the expected function, then it's basically x times the positive coefficient. So if you wanted to minimize that, the optimum is going to be at -1. Okay. But now let's look at the gradients. Okay. So the gradients are going to be either 20 or -1, right? So if you take the negative gradient, that's going to be -20 or +1. So of course, the -20 gradient is pointing in the right direction. It's trying to take you towards -1. Whereas if you look at the other gradient, which is +1, it's actually pointing in the wrong direction. It's trying to take you towards +1. Okay. Unfortunately, what happens here is that the large and informative gradient occurs very, very infrequently. Like it occurs basically once every 20 times, right? So you go very, very infrequently, you're going to see a very, very large gradient which is pointing in the right direction. But most of the time, you're going to see a gradient which is pointing in the wrong direction. So mostly speaking, you're going to be going in the wrong direction. But you hope that maybe when you see the large gradient, you're going to get a course correction and you move back in the right direction. However, because methods like ADAM scale down the gradient by a square root of the sum of squares of the past few gradients, the magnitude of the large gradient is dampened, right? You're going to divide -20 by not only square root of 20 square, but a sum of other things as well, okay? So even though you have a large informative gradient in the right direction, when you scale it down by this exponential moving average, you end up making very little progress in the right direction, okay? So that's a problem. And because you only average, because the exponential moving average essentially averages only over essentially like a fixed size window, very soon you quickly forget that you actually saw a very, very informative gradient in the past, and you continue to make progress in the wrong direction, okay? So that's why Adam fails. I mean, that's basically the whole intuition behind the proof, and there isn't very much more to it. I mean, it requires a little bit of math to, I mean, it's not too hard to show that methods like Adam, RMS prop, and so on, any of these methods which rely on an exponential moving average, or essentially only use like a fixed size window of past gradients, is going to converge to the wrong solution, okay? Whereas we know for sure that SGD and AdaGrad will converge to the right solution. I mean, there's a little bit of a game here where you say that, okay, for any setting of parameters for Adam, I'll give you a problem instance where Adam will fail to converge. Okay, so that's the kind of game you're playing here. Whereas SGD and AdaGrad don't have this issue. You can set the learning rate of SGD to be 1 over square root t, regardless of the choice of the initial learning rate, and it will converge. Okay, so that's not a problem. Yeah. Momentum doesn't, no. Yeah. Are you asking if SGD with momentum will have an issue?
Yeah. Just SGD plus
I don't think that will have an issue. So the main issue is this rescaling by the square root of the past few gradients squared. So yeah, so I mean, the proof is very simple. We can extend it to any of these methods. Okay, so what you can show is the following. Okay, maybe the second theorem is a bit more interesting. So I mean, essentially encapsulate what I just talked about on the previous slide. So for any fixed setting of parameters of Adam, you can come up with a stochastic linear optimization setting where methods like Adam, RMS prop, et cetera, will converge to absolutely the wrong solution. I mean, they'll converge to the wrong end of the interval, whereas methods like SGD and AdaGrad and so on won't have an issue. Okay, this clear? Okay, cool. So that's fine. I mean, so we gave a counterexample. So what's the big deal? It still works in practice. So maybe at least, I mean, the hope is that at least we can, I mean, okay, if you look at the original paper of Adam by Kigma and Ba, there is actually a proof of convergence. So obviously there is a bug, right? So, so I mean, you can go through the proof and try to understand, what happens when you run this example, and you realize that the primary reason for non-convergence is that if you look at, so essentially what is the learning rate. Okay, so if you look at the effective learning rate, which is going to be your base learning rate alpha or eta, or whatever you call it, divided by the square root of the sum of squares of the gradients. So the effective learning rate, ideally standard optimization theory tells you that the effective learning rate should be decreasing with time, okay, or at least not increase too much, all right? But what can happen is, at least in the example that we constructed, Adam can quickly increase the learning rate from iteration to iteration, and that's a problem. So typically, we do need a non-increasing effective learning rate for convergence, and this is critical. Adam has all sorts of hacks on top of this RMS type of update. It also adds like an epsilon in the denominator, which you have to tune as well, and so on. Anyway, the problem still persists. You can still show non-convergence regardless of all of these hacks. It helps a little bit to stabilize the learning rate to add this epsilon to the denominator. But I mean, the fundamental problem still remains. Okay, so again, this is all in theory. Does this have any implication in practice? Well, actually, the main reason we started thinking about this thing was actually we were working on a very, very large-scale optimization problem at Google. So we're trying to build a model for working with billions of possible output classes. So it was a billion-way multi-class problem. And in those situations, you're because of various reasons of sampling and so on, you get an extreme sparsity in the gradient updates. And when you have that situation, when your gradients, when you have extremely sparse and infrequent updates to your gradients, you run into the same issue that I explained in my counterexample, where very, very infrequently you get a very, very informative gradient. Most of the times you're just seeing nothing. And then ADAM doesn't work because of the limited size averaging makes it forget that you ever saw an informative gradient. Okay? So we actually saw this problem in practice, which inspired us to think about it. AdaGrad works fine for this problem, so we actually had to use AdaGrad to make the model converge. So this is not just a theoretical problem, it actually happens in practice as well. Okay, so how do you resolve this problem? I mean, there's a few simple things you could do. Either you can fix the beta 2 parameter in the denominator and just change the update so that the learning rate keeps decreasing, which is what we call AMSGrad. That's a new algorithm. Or you can use the same algorithm, ADAM, and keep increasing beta 2 with time. Okay, so that means you have to again tune a few more hyperparameters. You have to have a schedule for increasing the beta 2 parameter, and that becomes a bit more messy. Anyway, the idea is to always ensure that the effective learning rate is not increasing, and either of these two methods will do it. The one we like is this method called AMSGrad. It's probably the first thing you would think of is like if you want to fix ADAM, which is if you wanted to make sure the learning rate does not increase, then you basically cap it at the previous learning rate, right? So if at any point the learning rate threatens to go above the previous learning rate, then you just cap it at the previous learning rate. Okay, that will ensure that it's not increasing, and that can be rewritten as this kind of max form of update in the denominator, and it's called this is a method we call AMSGrad. And here the learning rate is automatically decreasing because of the max operator, and then we can actually prove that it converges. Okay, so it has average regret about 1 over square root t, so it has the same kind of convergence as HGD. Okay, so that's AMSGrad. Yeah, and this is, by the way, a plot of what happens when you run ADAM and AMSGrad on the same. Oh, sorry. Should I finish?
I'm just not a troll question, but it's okay if the learning rate increases at the beginning, right?
Yeah. Yeah. Yeah.
Make that.
Yeah, that's a good point. I mean, usually people have this epsilon parameter, which, fine. So, yeah, okay. Yeah, more problems. Anyway. Okay, so here's ADAM and AMSGrad. So again, the simulation here is on the bad example that I showed you, the simple linear optimization setting. So you can see that ADAM converges to the wrong solution, goes to -1 straight away, and AMSGrad actually does converge. Okay, good. So this is a little bit more confidence that our proof doesn't have bugs, I think. Okay. Also, okay, so so now you might ask, okay, how does it work in practice? Well, since it's like a minor tweak of ADAM, as you might expect, it works as well as ADAM when ADAM works. So whenever ADAM works, this works well as well. But here's a method which has a guaranteed proof of convergence, so why not use it? So that's our message. Frequently, we observe that it actually has better test performance than ADAM. I mean, okay, there's a slight improvement, and it has found implementations in all the standard deep learning packages now. Okay, so that's it. I have to. I mean, that's all for the first part. Any questions on this part? I don't mind troll questions as well. So, yeah.
So to use it in Keras, for example, you just say optimizer equals AMSGrad?
Yeah, I think there is like a flag where you say, yeah, you just turn it on basically. So, yeah. Cool. Yeah.
How does it compare with just a vanilla HGD or custom Gs?
That's a good question. I think, I'm not quite sure, but like ADAM usually outperforms SGD on tasks like these, and so it has similar performance. I would expect it's the same. Yeah. Okay, any more questions on the first part? Just checking time. Okay, so let me move to the second part. So this is a paper which appeared in NeurIPS last year. This work with Manzil Zahir, Devendra Sachan, who's at CMU, and Sanjeev Kumar and Sashank, who are all at Google. Okay, so the first method was, the first part was kind of pessimistic. It said, okay, why Adam might not work in as well. So this is trying to salvage it a little bit and at least give some bounds for its failure. So, the first paper actually motivated this paper, where we tried to understand, okay, we know Adam might not work, but can we bound how much failure it might suffer? So we tried to do like a first-order convergence analysis for Adam. First-order convergence. By that I mean, if you were to run Adam on a non-convex problem, would it actually converge to something close to a first-order stationary point? Okay. So first-order stationary points are something I think Rachel talked about as well, where we want to talk about a point where the gradient is small. Okay, and so we were actually able to come up with an analysis which basically shows that. So it has we get a bound on the squared norm of the gradient for Adam, which basically drops like 1 over t. So there's two terms. So there's a 1 over t term, which of course goes to 0. But then there's an unavoidable sigma square term, where sigma square is the variance in the gradients. Okay. So essentially, it converges to something close to a first-order stationary point, up to the variance in the gradients. Okay. This is something. This is nice in a sense, because what it tells you is that if you were to reduce the variance in your stochastic gradients, you might actually get better first-order convergence. And an obvious way of decreasing the variance in your stochastic gradients is to increase your mini-batch size. So if you use larger and larger mini-batch sizes, then the variance will drop, and then you will actually be able to prove convergence to first-order points. Okay, but again, that's another thing that you have to tune and so on, so it's a little bit messy. Okay, so actually the main work that came out of that was in this paper was a new optimizer, which we call Yogi for some reason, which was motivated by the fact that the reason Adam fails is because it might increase learning rates very quickly. So this is in the grand tradition of deep learning, where we try some nice heuristics and they work. So here is one. So we noticed that the bad convergence behavior of Adam is because of catastrophic forgetting of informative gradients. So essentially, because you are averaging over a fixed size window, if you have informative gradients that occur only infrequently, you're going to forget them very quickly. So how do you prevent that? How do you have essentially infinite memory? So here's one way to do it. You want to stabilize our learning rates using something like a additive rather than a multiplicative update. So here's the tweak that we're going to do. So remember that adaptive methods update the parameter by taking the stochastic gradient gt and then dividing it by square root of something. Okay, let me call it vt. And AdaGrad is simply the situation where the vt is updated by taking the sum of all the squares of the previous gradients. Adam is where you take a convex combination between the previous vt and the current squared gradient. And the new method, Yogi, is something where it has like really weird-looking update rule. So you might wonder what is going on, and I don't have a good answer. But I can give you a few, I guess maybe some bit of intuition. So notice that in Adam, the previous vt minus 1 is damped down. It's multiplied by beta 2. So essentially, you can trying to start forgetting the previous gradients. In Yogi, the coefficient multiplying vt minus 1 is 1, which means you don't forget. And then there's some weird update which depends on whether the current gradient square is bigger than the past vt or not. If it's bigger, then you will increase vt a little bit. If it's smaller, then it actually decrease vt a little bit. Okay. So the motivation for the second part is that, okay, we're going to try to mimic Atom as much as possible because we know Atom works very well. But we're still going to try to build in infinite memory. Okay, so this is all super duper hand wavy. Okay, but I want to explain what I mean by stabilized learning rate. But first, I want to say that, okay, even though we have this really crazy update rule here, it still has the same first-order convergence bound as Atom. So again, we can show that for this method, it converges to within say sigma square of the of a first-order optimum point, stationary point. Okay, so that's at least a sanity check here. But the real demonstration of why it might be useful is in this plot, where we can come up with a simple simulation where, okay, how do I actually, let me see. Okay, so the first thing here basically shows magnitudes of gradients over time. And then the second plot here basically shows how the denominator in Atom changes. So the denominator decreases rapidly. And because of that, the effective learning rate in Atom can increase rapidly. Okay, so it goes up. So if you do the same stuff with the Yogi update rule, you notice that the learning rate, I mean, it does wiggle up and down a little bit, but it's kind of stable. It doesn't decrease too rapidly. And because of that, the learning rate remains pretty stable. It doesn't increase very rapidly. So that's nice. We know that that increasing learning rates too quickly is a bad idea. But the real proof, I guess, is in the experiments. So we use this method for basically any, I mean, I don't know, anything you could think of, and obtain state-of-the-art or better performance. It's actually generally beat state-of-the-art, in fact. So for simple data sets like curves or MNIST, we beat state-of-the-art with very little hyperparameter tuning. And I guess, I mean, the main reason we believe is because of the stability of the learning rate. Again, this is another sort of examples where we just beat state-of-the-art by very little. Okay, so again, one of the points that Rachel was making in her talk was you want a method where you don't have to do a lot of tuning, right? So here, I think we have a recommendation of a few parameter settings, like 2 or 3, and they just work out of the box. I think maybe the most telling experiment is this one for training this something called the transformer model, if you have seen it, for a neural machine translation task. This problem, I mean, this model is notoriously hard to train. In fact, the people who proposed the model had to actually design a custom scheduler for learning rates. So they had to handcraft this, kind of what you're talking about earlier about you drop the learning rate until you reach a plateau, and then you suddenly drop it by a factor 2 or something. Anyway, so they had to do all these tricks to actually make it converge. Yogi works out of the box. It actually gets better than state-of-the-art for the transformer model, and also leads to 2x speed up. So I think that's pretty cool. Okay, yeah.
Why do you want to stabilize for typical gradients around V? Like, you could have another parameter, like the
Yep.
sine of GT squared minus alpha.
Yeah, I agree. I mean, there's many heuristics you can think of. This one works, so.
But you try at least like 2 VT minus
I'll have to check with the guys who tried the experiments, but yeah, I mean that all makes sense. I mean, so like you might want to be within VT and VT twice VT, which is what you're suggesting, right? I agree. It makes total sense. Yeah.
Beta 2 is 0.999. That's a good choice. So you're just adding just a tiny bit of the current.
Yeah, you're adding only a tiny bit of the current, which is what Atom does as well. It always adds a tiny bit of the current one. It's mostly putting it right on its past one. So yeah. So. All right, I think that's all I have in the second part. So, doing pretty good on time.
Is that GitHub or is it?
This, actually, that's a good question. This, I believe there are plans for open sourcing, but it's pretty easy to implement. I'll check with my co-authors. It might be in TensorFlow soon, So, okay, maybe this also kind of. I think you had a question yesterday about whether any of this theoretical stuff has practical implications, and I believe maybe this is one demonstration of that, so I'm pretty proud of it. Okay. All right, so I'm going to go to the third part. I mean, before I do that, questions? Yeah?
How does this algorithm compare to the AMS?
Yeah, I think that's a good question. So I think, I mean, it's definitely better than AMS grad because, the main feature here is that you require very little tuning of hyperparameters. Just use the ones out of the box, and it just works. So,
Maybe another question. Did you
yeah.
think about like a continuous time limit if you were taking? Is there
Ah.
just some diffusion limit?
No, we didn't think, but that's, yeah, I wonder what it is. Yeah. That's a good direction to pursue. We didn't think about it. Any more questions? Okay, so I'm going to move to the third part of my talk. This is joint work with Matt Stabe, who's from here. He's a student at MIT. Shashank Reddy and Sanjeev Kumar and Suvrit Sra, who's, I think Suvrit's also here, but I'm not sure if he's around. Anyway, so, okay, so this is super new work, just recently submitted to ICML. It's also available in arXiv. Okay, so this work aims to understand why Adam actually works, things like Adam work. I mean, sure, we had a super pessimistic view of Adam in the last couple parts of my talk. So here we actually want to really try to understand it better. Okay, so people have tried to understand why Adam works, and there have been numerous explanations. So the first one is that, okay, it's the natural non-convex modification of AdaGrad. So, I mean, that it kind of makes sense. I mean, in AdaGrad, you take the average over all the path gradients. In the non-convex setting, when you're kind of moving from valley to valley, you might only want to average the past few gradients. So it makes kind of sense. Yeah, so yeah, but I mean, there's no like good theory for this. Okay, so it makes intuitive sense, but there isn't any good theory for this. Another explanation. Okay, so. So there's no theory for actually understanding how to forget and why we should forget. The main explanation we're going to propose in this work is that what Adam is trying to do is not so much forget very old gradients, but it's trying to approximate the covariance matrix of the current gradients as well as possible. Okay, so. I mean, so what I've shown on this slide is something kind of simple, which is to say that we're going to try to approximate the population covariance matrix of the current stochastic gradients. And the way we're going to do it is by an exponential moving average over the past few gradients. Okay? So I'll go into more details of this, and I'll explain why we think this is a nicer view of what Adam is doing. Okay. Oh, by the way, I should mention here that we're looking right now at the full matrix form of Adam, where essentially you don't do like a per feature scaling, but you multiply the gradient by something like the inverse square root of this exponential moving average over the past outer products. Anyway, that's a mouthful. It does that. Okay, so. All right, so that's an explanation we're going to try to propose. But before we do that, I want to talk about two other explanations that people have mentioned in the literature. So one, which came from the original paper of Kingma and Ba, is that Adam tries to approximate the natural gradient method. Because, and while while it might be so the idea here is that the expectation of GG transpose is an approximation of the Fisher information. It is this approximation is only true near the optimum, and even if you wanted to try to use, even if you were to try to take the motivation of natural gradient, it still doesn't explain why we actually take the inverse square root and not the inverse. Okay, because natural gradient methods take the inverse of the Fisher matrix to precondition the gradient. Okay, so. So if you were to take motivation from the natural gradient method, then we would try to have an update rule of this kind here, where we multiply the gradient by the inverse of the GG transpose matrix. But what we actually really do in practice is something like expectation of GG transpose to the minus half times G. Okay, so why this minus half versus minus 1? Okay, so this explanation doesn't really seem to be very accurate. And even worse, when you're in the noiseless case, so for example, when you have very large mini batches, when there's no noise in the gradients, then your update rule looks something like this. It essentially looks like x minus eta times gradient divided by squared norm of the gradient. So this is going to become extremely unstable near the optimum point, near stationary points, because then the gradient is going to become close to 0, and you're dividing by the squared norm of something close to 0, and you're going to oscillate wildly. So there's no reason to expect that this kind of update rule would be actually a good method. Okay, so we don't think natural gradient is the right explanation for Adam either. Okay, so one empirical observation.
Is that a justification of using the minus 1/2 power instead of the pseudo inverse or something?
What is the justification?
Would you still have this problem if the approximation you got was only first power of the norm of G underneath, and if you were taking a different?
No, because both G and the norm of G would go to 0 at the same rate, right? So, but I mean, if you assume that eta is small enough, I mean, if eta is small, then it only bounce around up to eta, right? Which is fine, which is what always happens. But here you're actually explode. You go to infinity, even if eta is.
Right.
So. Okay. So here's an empirical observation which guided the analysis. So we have noticed in the past that adaptive methods tend to escape saddle points faster than SGD. Now, this is a controversial statement because we have no idea if you're in a saddle point or not. But we have noticed that SGD gets stuck at some point, and things like Adam tend to escape that kind of plateau region very quickly. Okay. So this is a super, heuristic-y observation, and this is what we're going to try to explain. Okay. By doing the following thing. Okay. So people have observed in the past that taking the diagonal form of Adam, which is where you do the per feature scaling of the coordinates, it tends to normalize variance in each of the the cardinal directions. Okay, along the standard basis vectors. So a simple observation is that if you actually take the inverse square root of the covariance matrix and multiply it by the stochastic gradient G, then when you're near a saddle point, because the expectation is close to 0, when you do this product, you're going to end up with isotropic noise. Okay, does that make sense? Okay, so what we are saying here is that near a saddle point, when you take the inverse square root of the covariance matrix and multiply it by a stochastic gradient, what you end up with is a zero, essentially a zero mean identity covariance random variable. Okay, so you have isotropic noise. That's nice because if you're in a saddle point, and if you have isotropic noise, and if there is a direction in which you can escape, then by random chance you will find it, and then you'll escape. So that's like the high-level idea. Okay. So our view here is that adaptive methods like Adam can be thought of as preconditioned SGD, where we're preconditioning the stochastic gradient by the inverse square root of the inverse covariance matrix. Okay. So why should this help? Okay. So again, this is kind of a formalization of what I was saying earlier. So if you're near a saddle point, you might have you might be in a situation where there is an escape direction. So here's a simple like two-dimensional function where at the saddle point you have the Hessian has one eigenvalue which is 1 and one which is minus delta, where delta is a very, very small quantity. And let's say the covariance of G, the stochastic gradient, has that form where you have along the escape direction you have very little noise. So there's a sigma square noise in the escape direction. So if that happens, then it's going to take you a long time to actually get enough noise to move in the escape direction. Does that make sense? All right. So we can, I mean, simulate this and it works, just, I mean, as you might expect. So in the specific example that I showed you where you had like a quadratic function with a slight negative eigenvalue, when the stochastic gradients have a reasonable amount of noise in them, when sigma squared is something like 0.01, they escape reasonably quickly. So this is where they kind of plateau out for a while, and then they escape, boom. But when the noise in the stochastic gradient goes down significantly, the amount of time it takes for the stochastic gradient to descend to escape is much longer. So it takes much, okay? You do the same experiment with adaptive methods like ADAM or RMSProp with the idealized form where you actually take the inverse covariance matrix, and you see that essentially they escape just as fast regardless of how small the noise in the stochastic gradients is. And that makes sense because by multiplying the stochastic gradients by the inverse covariance square root, you're whitening out the noise, so it doesn't, I mean, you're essentially, it doesn't matter actually how much noise was there to begin with, you're amplifying the noise in the right directions. Make sense? Any questions? Yeah.
So if you have the non-full matrix version and it's coordinate lines, does it still stay the same?
Yeah, it does. Yeah, you're right. So it's a little bit trickier in that situation, of course. Yeah. I mean, we have some bounds in that case as well. The dependence on the problem parameters is worse and so on. But can we come to the bounds? Okay. Any other questions? So far I've only given intuition about why things should work. Okay, so this is something that people have, this kind of paradigm for escaping saddle points is pretty common. People in the audience have already used this method where whenever you're in a saddle point, you try to add some isotropic noise to escape from saddle point if you have an escape direction. Because once you're slightly away from the saddle point, because you have an iterative algorithm, you will quickly make progress away, okay? And so again, this only says what I was saying earlier, which is when you precondition stochastic gradient with the square root of the inverse covariance, you end up with isotropic noise. So you don't need to worry about adding some additional isotropic noise to give that initial kick out of the saddle point. Okay. So people have studied SGD and its property and how it escapes saddle points as well. SGD with this modification where you add some isotropic noise. So the way these two algorithms, SGD and adaptive methods, escape from saddle points is slightly different. So SGD depends on the noise shape for the initial kick. So if the noise is aligned with the escape direction, then you will escape. And after that, you don't have any dependence on the noise. In adaptive methods, you actually have no dependence on the noise in the stochastic gradients for getting out of the saddle point. But after that, you do end up with some dependence on the noise in the stochastic gradients. Okay, so the analysis becomes a little bit tricky because of this reason. Okay, so I'm going to give bounds now. I have how much time? 2 minutes? 3 minutes? Okay, cool. Okay, so I just wanted to mention what we're talking about here. So for concept optimization, either we talk about epsilon optimal points where we come to within epsilon of the optimal error. For non-convex first order optimization, we want the norm of the gradients to become small. For for non-convex second order optimization, we also want the point at which we converge to. If you look at the Hessian at that point, it should have eigenvalues that are not super negative. Okay, so they should be bounded from below by minus square root epsilon. Okay, so those are standard parameter settings for talking about optimization convergence bounds. So the first thing we can say is that if you look at the idealized adaptive method, where you actually take the covariance matrix, invert it, take the square root, etc., either diagonal or full matrix, we have slightly different bounds in both cases. They actually converge to a second order stationary point in something like epsilon to the -5 time. Okay, and of course I'm hiding a bunch of constants. So the constants depend on how well or how poorly the precondition aligns with the Hessian. There's some other bounds on the norm of the gradients, etc., etc. So standard things. So now we can actually, now by separating out the idealized adaptive method from the estimation process, we can talk about ADAM in a different manner. So note that the theorem that I showed you on this slide actually relies on having access to the true covariance matrix. So of course, we cannot compute it directly. And one trivial way of doing that is to like repeatedly sample at the current point, many stochastic gradients, and then average them and take an invert them. Of course, that works, but it's wasteful, computationally expensive. You have to do many iterations. But then you notice that if you have a small step size in your optimization method, then the iterates are not moving very much. You kind of move very slowly. So a stochastic gradient at the current point is going to be so if you look at the stochastic gradient at like 1 point past, it's also going to be roughly a stochastic gradient for the current point with some bias. Okay, the bias is because you're not at the current point, you're at the previous point, but the bias is small because you have a small step size. So you can try to think of this as a completely separate estimation problem where you have a sequence of iterates which are changing slowly. You want to estimate a function of these iterates, namely the covariance matrix. So how should you optimally average the noisy observations in the past so as to minimize the estimation error? You can cast it as an optimization problem. So if you use exponential moving averages, you can do the analysis, and it gives you a prescription for beta 2, this parameter for ADAM. And for the specific case of exponential moving averages, taking beta 2 to be 1 minus step size to the 2/3 minimize estimation error. So you can come up with bounds like this. So that's our prescription. And so now we can glue these two parts together. So first part is that we know that idealized methods which use the exact covariance matrix will escape. And now we can estimate the covariance matrix by taking an exponential moving average of gradients in the past. So and then also gluing these parts together, where we look at the error that you get from the estimation and the error that you get from these conversions. You can tune the parameters properly, and you can show also that real methods like RMS prop and ADAM and so on converge to second order points as well. Okay, so that's the main result. There's some bit of fine print here because you have to adjust the step sizes a little bit here and there, but it's nothing immoral here. So okay. I think that's it. So thank you. Yeah. Okay. That's it. Thank you.
A couple of quick questions.
Yeah.
Is there an assumption that the covariance, the stochastic ratings, is full rank? Because I'm thinking about when the noise comes from sampling from your training set.
Yeah.
You have endpoints.
You're right. There is a
Covariance
yeah.
is number of parameters, so it has to be.
Yeah. That's true. Yeah. So we do. Needs to be full rank, or at least in the escape direction. It needs to have reasonable. Yeah. The simplest way is to assume full rank with bounded eigenvalue from the bottom, or you can assume that in the escape direction it has good coefficient. So yeah.
So I was a bit confused because usually, like in pretty much any computation, there's no way for us to store any second-order information due to another memory that would be required.
Yeah.
But in like very bad cases, you can have essentially different covariance matrices whose best diagonal approximation is a constant times identity.
Yeah.
I don't really understand like what do you need in this case, and like does it even help?
So, okay, I'm not quite sure I understand your question. So you're saying, I agree, we can't usually show the covariance matrix. That's too much memory. So instead, we approximate it by the diagonal.
Right,
So
if I have my covariance matrix, which is literally a rank 1 matrix that's rotated, the best diagonal approximation is a constant times identity, which doesn't help.
yeah. No, you're right. So the diagonal approximation can be super loose, and it might not work either. But so our result for the diagonal case actually has some extra conditions that I haven't talked about here. But yeah.